Okay, now let's talk about what happens to voltage and current. When we first turn on our voltage source, let's say we first hook up the battery, it's going to start putting charges on top of this plate, which is then going to force charges away from this plate and begin this flow of current. Current starts to flow immediately. It's largest at the start, and gradually as the charges fill up on this plate, there will be no current at the end when the plates are all full. So current begins to start immediately and is largest at the beginning and then falls down to zero. Meanwhile, okay, that's what I just said. So current starts immediately, but then when the plates are full, it goes to zero. So what does that look like to current? Here's a picture of an interesting circuit where we have a switch that's going to take this 10-volt battery and turn it on to start charging this capacitor. We know that the current is dq dt, but that's also equal to the capacitance times the change in voltage with respect to time. So as I turn this on, let's see what's going to happen. When I first turn it on, it's going to go up to its peak current, and then it's going to gradually go down to zero as the plates get full. In fact, its peak current is going to occur up here when the capacitor is effectively a short circuit. So look right here. When we first start it, all the current can go into that capacitor. At the very beginning, when we've had a big change, this capacitor acts like a short circuit. So what would the current be? It would be this voltage divided by that resistance. And in fact, oops, right there, that's what it is. This is what it would be at time t equal to 0. And then we have this exponential decay. The speed of the decay depends on something that we call the time constant, tau. That is equal to R times C for a series resistive capacitive circuit. If I had, for example, R is 1 kilo ohm, C is 1 microfarad, and this voltage, this is exactly what my current would look like, starting out at Vs over R and ending at 0. The time constant tells us that as this exponential decreases, it will reach 36% of its original value at the time constant tau equals Rc. Okay, now what happens when we first turn on the voltage? Well, originally there are no charges on the top plate, there are no charges on the bottom plate, and so the total voltage across here would start out at 0. But as we gradually add up all of these charges, then there's going to be a large voltage at the end. So the voltage is the integral of the current over time with the capacitance inverted. So right here's my case. I'm going to be integrating the current over time. This is what it looks like. My voltage starts out at 0 and it ends up at Vs. The voltage is 1 over the capacitance times the integral of time, and if you look at that, that's going to be Vs times 1 minus e to the minus t over tau. Again, it's the same time constant. So the voltage reaches 66% of its value at the time constant Rc. So here's the answer to what does a capacitor do to a voltage and a current. Here's the current plot that we looked at, and here's the voltage plot. Steady state would be long time, like after the switch had been closed for a long time, and that would say there would be no current and that there would be a large voltage. At time t equal to 0, when there's a very big change, the capacitor acts like a short circuit, but time t equal to infinity, when it's all charged up, it acts like an open circuit. Now what are the implications of that? When we have something that we want to charge and discharge, instead of being able to do a square wave like we might have liked, we always end up with some stray capacitance that make our square wave look like this charging-discharging curve. How do we use capacitors? Here are two examples where we use them for energy storage. This disposable camera, for example, has two batteries and a capacitor inside in order to make the flash that you use when you take a picture. The capacitance between the clouds and the earth is what creates the ability for lightning to strike. We can also use capacitors to stabilize power, for example, to reduce ripple. Here is a case where we put in a power supply, and let's suppose that sometimes it was a little more than 9 volts and sometimes it was a little less, but that our circuit over here wants exactly 9 volts. In that case, this capacitor can take a little bit of that away when it's too high and return a little bit back when it is too low. The capacitor is effectively storing the excess and releasing when it is needed. Now let's talk about low-pass and high-pass filters. A low-pass signal is going to allow a constant value to go through, but not the high-frequency noise. So here is a series RC circuit where, remember that if I have a change, a fast-changing thing, that this thing acts like an open circuit. So it allows the low frequency to go through, but not the high frequency. Here's another example. What does this look like without the capacitor? It looks like an inverting amplifier. Now let's suppose that we tried to send a DC value through. Well, the DC value, this capacitor still acts like an open circuit, so it just acts like an inverting amplifier that you've always seen before. The low-pass signal goes through. But now what if I wanted to send a fast-changing or high-frequency signal? In that case, the capacitor would act like a short circuit. I'd be shorting out my R2. Remember what the amplification for a inverting amplifier is? Remember that the gain is equal to minus RF divided by RS, and that in this case, the RF is R2. What if I made RF equal to 0? Then my gain would be 0, so the high-frequency signal that would come out would be 0. The capacitor allows the low frequency to go through this circuit, goes through R2, but takes the high frequency through here, makes the gain equal to 0. This allows the capacitor to work as an integrator. Notice here's the RC circuit right here. It's taking this square wave and it's producing this output. Remember what integration does? It finds the area under the curve. When I first made my step up, the area is 0, and gradually, as I'm adding up the area of the curve, it builds up to the maximum voltage. Then, when I take a negative value, it starts subtracting off that value. So there's my charging-discharging curve. I can literally use this capacitive circuit to integrate signals that are coming in. Here's a high-pass filter design, or a DC block. In this case, notice I've just switched the location of my capacitor and my resistor. If I were sending a DC signal through, this capacitor would look like an open circuit, and my output voltage would be 0. Nothing would come out. What if I had a high-frequency signal? Then this capacitor would act like a short circuit, and the full voltage would come out. Now here's my inverting amplifier again. Remember that the gain is equal to minus RF, which is R2 in this case, divided by RS, which is R1. Well, if I have a DC signal, my RS is infinity, and so my full voltage comes out. If I have an AC, or a very high-frequency signal, I have a short circuit, and that means that I get no frequency, no signal out. So high-pass signals come through, but low-pass signals do not. That allows me to do differentiation. That means that I want to emphasize the changes. Here's an up and here's a down. If I did the derivative, I would see this, and I would see that. Well, this is what my capacitor does. It smooths it out a little, but there's my first step, and here's my second step. This is the differentiation of the square wave. So basically, we have covered these 4 topics. What is a capacitance? How does it relate to current and charges? How do the various parameters of the capacitor matter? And what does it do to a voltage and a current? Thank you very much for your attention.